Hello friends, welcome to Scientific Study for You. I am Apuru Pathak and in this video we are going to discuss the magnetic quantum number. So let's get started. Okay, in the previous videos we have seen that the principal quantum number n describes the shell in an atom and the azimuthal quantum number L represents the subshell and describes the shape of the orbital. Okay, the magnetic quantum number represents the possible orientations of the orbitals in space. Therefore, the magnetic quantum number suggests the possible number of orbitals for a particular value of L. It means that basically the magnetic quantum number tells the possible number of orbitals in a particular subshell. Okay, like for a particular subshell, how many orbitals will be there inside it. Alright, it is denoted by M. M can have values from minus L to L via the integral values between minus L and plus L. Now pay attention here. Okay, you all must have gone to a railway station. The announcements are done in a way like the train number 12365 goes from station A to station B via stations X, Y and Z, which means that the train will start from station A and train will go through all the stations between A and B and finally reach its final destination to station B. Okay, similarly the value of M will start from minus L and it will take all the values between minus L and plus L and it will finally end at plus L. So minus L and plus L are the endpoint values. Okay, for example when L is equal to 0, the source station and the destination station are same. That's why there is only one value of M, which is 0. Okay, when L is equal to 1, the value of M will start from minus 1 and it will end to plus 1 while taking all the values, integral values between minus 1 and plus 1, which is 0. Therefore there are three values of M for L is equal to 1. When L is equal to 2, the value of M will start from minus 2 and it will end to plus 2 while it will take all the values between minus 2 and plus 2. Okay, therefore there are 5 values of M for L is equal to 2. For L is equal to 3, the value of M will start from minus 3 and it will go up to plus 3 while taking all the values between the minus 3 and plus 3. That's why there are 7 values of M for L is equal to 3. Okay, now try to understand this figure. Actually, in the previous video I have already introduced it. Now again I would like to tell you the outer blue color represents the shell or energy level, which is denoted by principal quantum number n. Okay, the outer blue color, it represents the shell. Okay, the inner red color box represents a subshell or sub energy level. Okay, it is denoted by azimuthal quantum number L. Okay, and the inner green box inside the subshell represents an orbital. Okay, so make this picture in your mind very clear. This is the shell, the outer big box with blue color. Okay, the inner red box is a subshell inside the shell. Okay, and this green color represents the orbital inside the subshell. Okay, now let's see a few examples. All right, in the first example, as you can see, again there is a big box which is the shell represented by principal quantum number n, and inside this big box there is another red box which is the subshell, and for this subshell the value of L is 0. That's why it's a S subshell. Okay, and for L is equal to 0, there is only one value of M, which is 0, as I have discussed in previously. Okay, that's why there is only one possible orientation of S orbital in the space. Okay, as you can see, it is spherical. Okay, symmetrical, so it's similar in all directions in space. Okay, it's spherical S orbital. Therefore there is only one S orbital in a subshell. All right, the other example, again this is a big box. Okay, it is a shell, and inside the shell the red box represents a subshell, and for this subshell the value of L is 1. That's why it's a P subshell. Okay, and for L is equal to 1, there are three possible values of M, which are minus 1, 0 and plus 1. That's why there are three possible orientations of P orbital in space, which is Px, Py and Pz, as you can see from the diagram. Okay, that's why there are three possible P orbitals in P subshell, as you can see, three P orbitals. Okay, now the next diagram. Now in the next diagram you can see that again a big box, and this is a shell, and inside this big box there is another red box which is the subshell, and for this subshell the value of L is 2, that's why it's a D subshell. Okay, and for L is equal to 2 there are 5 possible values of M, which are -2, -1, 0, +1 and +2. Okay, that's why there are 5 possible orientations of d orbital in space. As you can see, dxz, dxy, dyz, dx square minus y square and dz square. Okay, that's why there are 5 d orbitals existing in the d subshell. As you can see from the diagram, there are 5 d orbitals existing in the d subshell. Similarly, you can calculate for the f subshell and the g subshell. Okay, very easy. So we can conclude that from all this that the total number of orbitals in a particular subshell is given by number of orbitals equal to 2l plus 1. Okay, which means that in a particular subshell there are 2l plus 1 orbitals, where L is the azimuthal quantum number. Okay, now we can solve a question on this. Like the question is, you can see, find the total number of orbitals in G subshell. Okay, so when L is equal to 0, it's a S subshell. When L is equal to 1, it represents a P subshell. When L is equal to 2, it represents a D subshell. When L is equal to 3, it represents a F subshell. And when L is equal to 4, it represents a G subshell. Okay, so for G subshell, value of L is 4. All right. So number of orbitals equal to we have seen just now that 2l plus 1 orbitals exist in a particular subshell, where L is 4 in this question. So 2 into 4 plus 1 equal to 9 orbitals. Okay, 9 orbitals. Therefore, in G subshell there exists 9 orbitals. Okay, it should be clear. It's very easy and simple. Okay, so I would like to conclude this video that in this video we have seen that the magnetic quantum number represents the possible orientation of the orbitals in space, and hence it represents the possible number of existing orbitals in a particular subshell. Okay, we have also seen that we can generalize a formula for calculating the number of orbitals in a particular subshell, which is given by number of orbitals equal to 2l plus 1. All right, so that's it. Thanks for watching.